Interesting.
So just to understand better, so you are making hypothesis. Is it already on some observed data, or someone needs to, go ahead and like make an experiment to prove your theory? I mean, maybe in general, like, would you, now you're on the computation side, would you consider, stepping out of your comfort zone and prove that your theory is correct?
So far, the most physical labor I've done in my PhD was assemble the chair on which I sit and code. But I'm not, my skill set is more in the computational and sort of like theoretical mathematical side of biology. We're open to collaborators, and we'd be excited to work on such a thing. And this very, very talented set of researchers.
Yeah, so I think what he glossed over is actually some of the evidence that he's talking about came out after their paper and was citing their paper. So basically, they inspired a group of biophysicists or polymer chemists, I guess, to actually produce RNA-only condensates and do catalysis with them.
I should say their work was done very well and independently of ours.
Yeah, so they might have already been working on this.
So Hoff and Dindo, those are the last names. They've done excellent work on essentially showing that RNA-only condensates can form with less than 20 nucleotides, and they can get simple catalysis to happen. They could speed up the reaction kinetics by a factor of 10.
But the $1 million question or thing that's missing is that they've done catalysis of certain reactions, but not of RNA synthesis. So in order for this to become like an evolutionary system, it has to catalyze RNA synthesis, and ideally not just random RNA synthesis, which you can still maybe live with, but you want to catalyze like copies of the thing that made the condensate, right? That would be ideal. And I think that's the big next, that's like the open thing that, if somebody could do, would be an enormous breakthrough that's kind of driven by this theoretical, he's giving out Nobel Prizes. But that would be like the big breakthrough that can be driven by this. I mean, I guess there's another way that it can work, which is that you can have random generation of sequences, but then their selection, the condensate, that happens like somewhere else, right? And then the condensate just selects the ones that it likes.
Like mutations, maybe?
No, you just have random, like let's say, there's been a lot of chemistry work showing that, nucleotides can form in prebiotic conditions, kind of like old Earth conditions. And so basically the idea would be that let's say you're forming random sequences of 4 or 5 nucleotides or something, and then the condensate is choosing the ones that it likes. And so it grows just by absorbing them rather than copying them. So that's another way that it can work, but that's not been shown either. So, right? Like, correct me if I'm wrong. So showing some kind of mechanism where the condensate can grow
changes the statistics, right?
Yeah.
So you start from uniform distribution.
Yes, and then the condensate plays with
would shape it in the right way.
Exactly. And then basically like the big question is, can somebody show if this theory is correct? And it does show like a path that's experimentally very interesting. Like in my opinion, when I read the paper, I was like, oh man, I wish I was doing experiments on this. Is can you do like some high throughput experimentation where you find a condition where you get one of these condensates that's able to either select or grow these short nucleotide sequences that basically copy it, with decent fidelity. But interestingly, the fidelity doesn't need to be that high because the error rate, this eigen threshold is basically, let's say if you have 5 nucleotide sequences, it's just 1 out of 5. So you need a 20% error rate, so which is still very low. It's much better than random, right? Yeah. But it's actually very realistic, maybe. Yeah. Or at least it feels realistic compared to an enzyme. Like if an enzymatic process with error correction gives you 1 in a billion, like it feels. If you were asking for 1 in a million, that would be like a little bit scary, but 1 in 5 feels better.
Well, do we know what's the catalysis process? What it needs to be?
So getting to this mechanism that would be, groundbreaking if it was elucidated, definitely, which is that if you can show, the $1 million question, if you can show that RNA undergoes replication in conjunction with a compartment, it could be a condensate according to our theory, but again, it could also be a vesicle if someone could show that it undergoes replication in conjunction with that, and that includes polymerization from a template. So when any nucleic acid is copied, it is copied in a way that you have a template, and each monomer is added one at a time in a 1-to-1 way on the template, right? And so this templated dependent process is essential for all life as we know it. If someone could show that happening in conjunction with the replication, growth, and division of a compartment, then that would be very groundbreaking. And so there is thermodynamics worked out of like what the energy cost of adding a nucleotide is onto a template, and it's like that stuff's known. And there's like various other sort of things known about like the stability of various base pairs and things of that sort. In the case of like secondary structure, there's something called the Turner rules, which is the rules of how pairs of bases that are adjacent with each other pair with other pairs of bases. And so this stuff is worked out. And what we need to now see is for this polymerization chemistry to be worked out, which is quite challenging. And that's one aspect. That's one possible mechanism. If this happened in conjunction with the condensate growth and division, upon which selection could be acted on, then the other aspect of it is that the condensate itself acts as a kind of classifier, a statistical classifier, where it can tell apart things that are self versus not self, because things that are self join the condensate and things that are not self do not join. And the more similar a sequence in the 4 to the k space is to itself, the more likely it is to join, and so on and so forth. So that is sort of this, polymerization independent selection. So it's sort of by selection, the condensate's able to maintain self identity independent of physical template based copying. And that would be interesting also if that was shown experimentally. And again, I'll add the caveat that the paper that Alan and I worked on was a theoretical biology paper. We developed a theoretical framework and we did some derivations, but we need experiments to really confirm this model. And that's now sort of where the next steps are.
And it seems like there were already experimentalists working on this. So to some degree, the timing is curious, which it often is in science, that a certain idea is ripe at that point. So do you think that these recent papers are going to give rise to an explosion in research in condensation? Are people excited? Surely Mike is excited about it and wants to spend his life now doing this.
Maybe it's Mike's
do you think this
PhD
is
topic?
Like, is this excitation palpable?
It's very hard.
It's
very hard to predict the impact of something. But what I will say is that part of it, you're right, is the timing and like the trajectory. But also, I think in the origin of life, the predominant origin of life community and the predominant bio community, the bio departments. There's sort of an attitude that's generally held by a lot of people, which is sort of like a reluctance to accept mathematical and theoretic methods, and sort of this tendency to, and not only that, just the theory in general is not emphasized as much in molecular biology. And this pattern sort of started in the 70s when they invented genetic cloning, I think. And before that, molecular biology was really created by physicists primarily in the 50s and 60s, who were very keen on making theoretic models and calculating things and deriving things. But really, once they got their claim to fame and all the success that happened in the 60s in molecular biology, we now have this period where genetic cloning was invented by Paul Berg and this took shape in the 70s, where biologists shifted their focus to just trying to clone everything and trying to really do all this physical labor. And there's nothing wrong with that, but it's just the theory sort of dwindled off. And this lack of theoretical emphasis continued to develop 70s, 80s. And most of the people that were trained in this period trained in a time where theory wasn't emphasized as strongly. And currently, most people running biology departments have this training. So there's essentially a lack of theoretical emphasis. And that's, I think, been a source of why there's been a lack of progress on the theoretical front. And I think now with the rise of computational biology, we're now at a time where we can really think about theory and actually try to go ahead and model. And of course, we need experiments just as much as we need theory. We need both. We really need both theory and experiment to really have the most impactful work that we can possibly have. Both are important. We need to do real biology, not just abstractions and sitting in an armchair. We need to do real work and we need
But
to
not
make
you.
real.